ahead and get started, and without any additional fanfare. This is the HDL Challenge Week 2. We are starting now on Thursday evenings instead of Friday as I had originally planned. So this is Thursday night for the second HDL challenge, for the second week of the HDL challenge. And we're going to be doing a number of things. Let's take a look at our agenda. If I can get my video to get my PowerPoint slide to move here, and it seems to be on the fritz for me for some reason. Let's see what's going on. Okay. Let's see if I can get it restarted, and maybe it'll go for it now. No? How about, no, it won't take a page down either. I don't know what's going on with me today, but I'm not having a lot of luck. Let's see if I can start from this slide. Well, at least I can get the slide up. The new HDL, we'll have a review of the new HDL editor that I have written for this series. We're going to look at last week's logic gates, or at least some of them. We're going to do a little bit of binary arithmetic. We'll look at this week's logic gates, the challenge for this week, and then we'll talk about the resources for today's challenge. And this little thing is just not going to work for me. So let me go out here, and maybe I'll have to do some kind of additional setup for this thing. Okay. Browse from an individual window. That's not what I want to do. Presented by a speaker on the full screen. Okay. That's what I want to do, but this is going to use presenter view, and that's not what I want. Maybe this will work. Let's try it from the current point. Okay, so far so good, and there we go. Our new HDL header is called HED, or head, for ease of use. And let me kick it off here, and, well, wrong thing. Let me kick it off from my program menu and get it up so that you can see it. This is the new HDL header. Maybe a little bit too small for you to see. I apologize for that. I'm not sure if there's a way I can zoom in on that. I don't think there is, at least not right now. And I apologize for it. But this is the HDL editor. And I have a link to it in our resources. Below this video, you can find the link to the homepage for the head editor. The head program is found, and download it from there. The first thing that you'll want to do when you come into head is to go into the settings menu and click resources, and in the program you'll get this window to pop up, and most of these fields will be empty, all of them except for the header text down here in the in this big text box that is pre-populated with a suggested header. But the one thing that you'll absolutely must do is fill out the save folder field. And this is where your HDL files will be saved as long as this folder address is in there. You can have more places in there, and as you select them, They will be available in a drop-down window here, and you can move back and forth between the folders as you like, but you must have something there because that's where the HDL files are going to be saved by default, and there's no other choice. The way this is designed, the files have to be saved into this default save folder. The components folder, I have it pointed to the built-in chips for the NAND to Tetris tools projects, and by having it point to that built-in chips folder, then all the chips that are predefined for NAND to Tetris will be available within head in a part of the in a part of the editor that will help you out to find those component names and so on. So that is a useful folder to have selected there. And then you'll click Save to make sure that those strings are saved. If you don't click Save, they will be used in this current session of head, but when you close head and come back, they'll be lost. They won't persist. To persist them, you must click the Save button. Head has a number of tab buttons here at the top to open up various pages for within the editor. And let's just load up a sample HDL file here, and I'll go into, let's just go into projects, and we'll go into projects 4, and I'll just there's not a HDL file there, nothing there either. That's interesting. All right, let's try a different project. Okay, here we've got a project, a CPU HDL will be interesting. We'll load that up, and apparently I found a new bug within head that didn't want to load up that particular file, so let's try another one. Maybe it will load up the memory one. Let's see if it'll get that one. No, it won't do that one either. I'm going to have to do some work on the parsing of this. So let me try one I know it will load. And that is right here. Projects 1, and we'll load up the AND HDL. And so now we have the input pins and the output pins. The parts list is empty because this is just one of the stub files for the course. The header text is parsed and loaded up from the file. So is the API text. If there's any description text, it would be loaded up here. And then a file view for the file as far as the inputs that we've had so far. All that we have are the ins and the outs, and there is no parts list here because we don't have any parts defined for this instance. But I'm just going to go ahead and go back and open another one that has some parts in it. And let's go back to, well, let's just load up the AND after all. This is from the, this is my AND gate that I've constructed for this week's challenge. And we have some parts now, and if I go back to File View, you can see the parts listed out here for the AND gate. So you have the parts list here. Each each logic gate is entered, and then the connections are listed here, but they're not editable here. If there had been a description for the NAND gate or the NOT gate in a comment beside the gate in the HDL, it would have been parsed out and listed here. The connections are edited over here on the right-hand side. You have each one of the connections, where on the left you have the part pin name, in this case A, B, and out, and then you have the external pins, and this refers to any wires or pins of the logic gate you're designing. So these are the inputs and outputs for the AND gate that you're designing, but they're not a part of the NAND gate that we're configuring here on the connections. And that's the way that we distinguish between those is the ones on the left belong to the part, and the ones on the right are external to the part in some way. And you'll note we'll see more of this as we go on tonight, but you'll notice later on that this can refer either to the inputs and outputs of the logic gate you're building, or to wires that are named within the component that you're building. And we'll see more of that as we go along today. This week's logic gates. Now we're going to look at the logic gates that we were assigned last week, and we'll use. Well, I think we'll use head. Well, let's see. Maybe for now, until I learn how to zoom into head, we'll use Notepad, because I can get Notepad to increase the size of the font. So let me find that, and get some preparation over here. And I'm going to go in here and load up from tonight's documents the files that I want to look at this evening. And I'll format there so we get exactly what we want. And we're going to look at the AND, the DMUX. Let's see. MUX or exclusive or not. And what was the other one more here? The 16-bit register. Oh, no, that's for this week. I'm sorry. The DMUX 4-way is the one I want to look at. There we go. Let me click open. And we're not going to look at them in the order that I brought them up here, but let me increase the screen size a little bit here. We'll start with the NOT gate, because this was the first one that you should do. You should have done this week. The idea is that we're starting off only with a NAND gate. And from that point, we're going to build everything we need to build out the CPU and the computer that we're going to eventually be building in this challenge. And the NAND gate is the only one we've got now, so we have to start with the simplest parts that we can design with just a NAND gate. And the only one I know of that you can do with just a NAND gate at this point, and let me point that out. Let me retract that. That's not true. You can actually build anything with a NAND gate. With multiple NAND gates, you can build anything. But it makes sense to start with these, with the simple ones, because then the simple ones are available for additional use later on in other components. So we're going to start with the NOT gate. And with the NOT gate, we have the definition of how the NOT gate works. The NOT says if N is true, or if this means if N is 1, then out will equal to 0. Otherwise, out will equal to 1. And the way that we're going to build this, and this is the way that they suggest that this should be done, is the NOT end is equal to NAND N. So we take the NAND and input two ends to it. The input to the NOT goes into NAND, and then the output from the NAND will be the output of the NOT gate. And that's how we've defined it here. We've got the end pin and the out pin. We've got one part, the NAND, and we set A equal to N and B equal to N. And the result of that is that the out is going to be the opposite of whatever N is. And thus it negates, it complements the value that is input. You'll get the opposite value on the output of the NOT. All right. The next one after the NOT is the OR gate. And the OR gate is if A or B is 1, if either one of these are 1 or both of them are 1, then the output will equal to 1. Otherwise, the output is equal to 0. A function A or B is equal to not A and not B. And so these two functions are equivalent to one another. And we have a NOT gate now. And, well, I'm sorry, we don't have the AND gate yet, so we can't do this one. Let's go make the AND gate first. Should have been here first. The AND gate is A and B. If both A and B are 1, then the output will be 1. Otherwise, the output is 0. Well, the NAND is just the opposite of an AND. So what we do is put the inputs to the AND gate to the NAND gate. A is equal to A and B is equal to B. And then the out goes to the in out, or the not out wire. And then in the NOT gate, the input is from NOUT, or in out, and then the output goes to out, and that produces the value that we want. And to test that, let's go to our folder here. That's not the one I want. I want to go to Documents and look for some reason I can't find that one very easily. To Tools, bin, oh, here we go. Hardware Simulator. And now we're at the Hardware Simulator. We're going to load up a script from, let's see exactly where we're at. Documents. NAND to Tetris projects 1. And we want to test the AND gate, so we're going to load up the AND test. And this is the AND test, and what it's going to do is load up the AND HDL. Go back to our notepad here, so when you see what we're looking at, we're testing the AND gate here. And this is going to load up the AND HDL and run these tests on it. It's going to set the A pin to 0 and the B pin to 0 and see what the output is. Then it's going to do 0 and 1, 1 and 0, and then 1 and 1, see what the output is for each one of these things. And so if we just click the run button here, it'll run through all those tests. And we get to the end of the script and the comparison ended successfully. So the AND gate is working fine. Now let's go to the OR gate. With the OR gate, OR is A or B. If either one or both of them are 1, then the output is equal to 1. Otherwise, the output is equal to 0. And as we mentioned, these two are equivalent. A or B is equivalent to not A and not B. And we're going to use the AND gate that we've just created, and we're going to use the NOT gate that we've created to implement the OR gate that we've designed here in this HDL file. So let's go back over to here, and we're going to load up the OR test. And the OR test is going to load up OR HDL and run its tests. And get to the end, and it says end of script, comparison ended successfully. We know that the OR gate is working the way it is intended to work. And so the OR gate logic we've got here is fine. And then the next one after the OR gate that we want to look at, let's see, we've had the OR, the NOT. We want to look at the exclusive OR gate. And the exclusive OR gate is not quite like the OR gate. There's some similarity, but the exclusive OR gate says that if either one of the inputs is 1 and the other is not 1, then the output will be 1. But if both of them are 1 or both of them are zeros, then the output will be 0. And this is the design that I've put in here. We've got, we're going to NOT the inputs of A and B, and that will give us the outputs of not A and not B. And we're going to take an AND gate, and we're going to give it A equals A and B equals not B. And that's going to give us the first output for the AND gate. That's not a very good name for that, but that's what I gave it. And the other AND gate is going to get the not A and B, and that's going to give us the second output. And then we're going to OR the two of those. A is equal to W1 and B is equal to W2, and then the output will be either a 1 or a 0 based upon the logic of the exclusive OR gate. So let's take a look at our hardware simulator. And there we go. And load up the exclusive OR gate test and see how that works. Exclusive OR gate will load up the exclusive OR and run the 4 tests that it can work on. And it ended here successfully. I should point out here that you can go in here by hand and do the testing that you want to do on your socket, your gate, like you as you wish. You don't have to use the test gates, and sometimes that's handy if you have a test that fails to work and you're trying to find out why it's failing. Then you can go in here by hand and change these. For example, I can go in there and change that 0 to a 1, and then I can look at the output. Well, I have to evaluate it, and we get the see the evaluation right here. Click this button to evaluate it, and that takes the inputs A and B, 0 and 1, and the outputs is equal to 1. And you can also see what the value is within the part that you're building. I can see what value is on the not A wire, what value is on the not B wire, what value is on the W1 wire and the W2 wire. These are the internal pins or the internal wires that are getting a value. These are the output values of the gate that you're designing, and then the input and values of the gate that you're designing. So it's really useful to be able to get to those parts of the data when you are having trouble with one of these HDL files. Let's look at one more, I think, and no, a couple more. We'll look at the Demux HDL, and the Demux HDL. You remember what a Demux is? This is a demultiplexer, and the purpose of it is you get an input and a selector. This is a 1-bit input, and you have a 1-bit selector, and the selector determines whether the input goes to the A output or the B output. And we've got some logic here where we take the selector and we're going to not that value. That gives us 2 values from the selector pin, a not select and a select value. We'll have not select and select value for inputting into these AND gates. And then for the A input, we send it to one of the AND gates here to we send the end in to the A input, and then the not select goes to B, and then the output will be here whatever the value of A is when not select is high. That is, when select is low, not select will be high, and that will give us the default value of the demultiplexer. And then the AND gate here gets its value also from in, and the select pin, and when select is high, then the value from in will go to the B output of the demultiplexer. And let's take a look at the logic at how that works. Demux, and run it. And this is a pretty simple logic gate as well, and so it completes successfully. And the last one we're going to look at is this Demux 4-way HDL. And basically this is just a little more fancier demultiplexer. It has, again, a single input with 1 bit. It has a select input with 2 bits this time. And these 2 bits are going to select the output of A, B, C, or D. And this is how I've designed the part. I take the select input And this time I just take one pin, and this is how you separate the pins of a multi-wire bus into its separate pins or separate wires. And these, unlike the MicroHard software we were using before, this is zero-based array. And so 1 is the high order bit for this 2-bit bus, and 0 is the low order bit for the 2-bit bus. And we're going to take the high order bit and we're going to feed it into the NOT gate. And so we'll have a NOT select 1 and we'll have a select 1 value. And we're going to put the NOT select 1 into the B of this and the input to the A of this and the output is going to go to in and NOT select 1. And this is the way I like to name the wires. And the wires tell me something about the value on this particular wire. This tells me that this wire contains the logic for when in is ANDed with NOT select 1. And so in and NOT select 1 is what that value is there. And this and then also takes the in input, but instead of the NOT select 1, it's going to get its value from select 1. And so we've got the output in this case equal to in and select 1. And then we've got 2 demultiplexers here, and we're going to take for demultiplexer 1, the in input gets its value from in and NOT select 1. For the other multiplexer, the in input is coming from the in and select 1. And then we give the same select wire, select 0, to the select input for the demultiplexer. And the result of that is the A is going to get its input from, or the A is going to be sent out to the A pin of the part. B is going to go to B. A from this demultiplexer is going to go to C, and B is going to go to D. And the result of that is that if there is a 1 on the in input, then based upon the 2 wires in select, it's either going to go to A, B, C, or D. And so what we're doing here is we're selecting a value between these 2 AND gates, and we're selecting a value between these 2 demultiplexers with the 2 select wires in this bus. And that produces the result that we want within this 4-way demultiplexer. And to show that, let's go take a look at the DMUX 4-way test. We did something similar, of course, for the DMUX 8-way. And so this is just a little more complicated. And the multiplexer is not that much difficult. We're not going to look at that, but we did something similar to these to get them to work the same way. So let's take a look at this one. It's going to load up the DMUX 4-way script and test it. I believe this is a little bit longer test. And it found that everything is working just fine, so the comparison ended successfully. And I think that's enough for us to look. I'm guessing that if you've done that much, the rest showed no difficulty for you. If not, then you may be still working on it, but hopefully this will help you to complete that. So let's go to our next part of our video today. We want to talk a little bit about binary arithmetic. Tonight's or this challenge is this week's challenge is all about adding and subtracting with a little bit of logic thrown in. Because computers are by design able to distinguish only between the on and off states, then all of their arithmetic operations are done in binary logic. And to design a circuit that performs these operations, we have to have some understanding of binary logic so that we can make these things do what they need to do. To design the circuits that perform these operations, we have to have that understanding. At least when it comes to addition and subtraction, binary arithmetic actually is pretty easy. It's easier. It is easier than adding and subtracting in decimal, because in decimal you've got 10 different digits that you have to know what the sums are when those digits are put together. With binary, you only have 2 digits that you have to know the sum for. And so it really is very, very easy when you think about binary arithmetic. Let's look at how to add up 2 binary digits. These are, and each one of these columns is an example of adding 2 binary digits, and these are all the possible combinations of adding 2 binary digits together, all the possible combinations. There are 100 different combinations, 100 different combinations of adding up decimal numbers in one column. Just 2 decimal numbers, decimal digits. There's 100 combinations, but there's only 4 combinations of a single column of binary digits. And so it should be much easier to understand than even in decimal notation. If you take a 0 and a 0 and add the 2 zeros together, you get 0. If you take a 1 and a 0 and add the 2 digits together, you get a 1. Similarly, if you take a 0 and a 1 and add them together, now it sounds like I said the same thing, but I didn't. If you take a 0 and a 1 and add them together, you get a 1. You still get a 1. And if you take a 1 and a 1 and add them together, what do you get? Well, if you're talking about one column, you get a 0 with a carry bit, with a carry over into the next column. Remember, in decimal, if you get more than 9 in the column, then you have to carry over whatever amount, whatever goes into the next column. Well, the same thing's true in binary. So if you add 1 and 1 together, well, 1 and 1 equals 2, but you can't, there is no decimal number for 2. 2 is represented by 2 digits, 1 and 0. And so with adding 1 and 1 together, you get 0 with a carry bit. Now, one of the components in this week's challenge is the half adder. And the half adder is able to perform the logic that we have shown here on this slide. Let's look at how to add binary digits, a single column of binary digits, if we are including a carry bit. Now, what we're talking about here primarily, I'm sorry, this I meant to mention this and I just failed to. Let me, I'm going to, can't. That turns my audio off too, so I can't hide my video. All right. I'll just move this over out of the way. How about that? You should now still be able to hear me, but you just can't see me. This shows you all of the inputs and the outputs for this operation. The input for this operation are the 2 bits in the above the line, A and B. One input is on this line, and the other input is on this line. And the output is the sum, which is on this line, and whatever carryout comes in. So this carryout is part of the logic of this operation. And the half adder would perform that for you. The half adder is able to take 2 digits, A and B, and give you a sum and the carryout from the operation, whether it's a 0 or whether it's a 1. Let's go now and look at adding 2 binary digits with a possible carry. Things get a little more complicated here. Things get a little more complicated here because now not only are we looking at these 2 bits coming in, we also have to consider the carry operation, the carry in to this operation. And so now there are 3 inputs and 2 outputs. Let's show that. 3 inputs. We've got the A, and this should be a B rather than an A, but we've got the A in this line, we've got B in this line, and then the carry in operation. These big number 1s above the columns represent another input, a 3rd input, which is the carry in. And for the outputs, we have the sum, which is the number at the bottom of each one of these, and the carry out, whether there's a carry out from the operation for each one of these columns. Don't think of these columns as being the right-hand side of a number. Don't think of these columns as existing all by themselves. Think of them as being part of a larger number that you're adding up, and there are 0s and 1s to the right and maybe to the left of these numbers as well. And so you might have a carry in from the column that would be right here next to this column here. And so what we're just trying to simplify it so that we can see how this operation works. In this case, there are 8 possible outcomes because we have 3 inputs, and 2 to the 3rd power is 8. Whereas in the first one, we had 2 to the 2nd power, which is 4 possible outcomes. This has 8 possible outcomes. And so if you take 0 and 0 and no carry, then the result is going to be 0. If you take 1 and 0 or 0 and 1 with no carry, then the result is going to be 1 for those columns. And if you have 1 and 1 to add with no carry, then the result, just like we showed before on the previous slide, is going to be 0 with a carry out, a carry bit over to the next column. Now the rest of these are the same values down here on the bottom, but we're considering with the carry in operation for them. And so here we have, if we have 0 and 0 and a 1 bit carried in, then that's going to be a 1. 1 plus 0 is 1. And then for this column, 1 plus 1 plus 0 is 2, or 0 with a 1 bit over into the next column carried out. And then 1 plus 0 plus 1, again, is 0 with the 1 bit carried out. And then finally, 1 plus 1 plus 1, with all of them 1s, you get, well, that's equal to 3. And 3 in binary is a 1 and a 1. That is, you have a 1 in the 2's column and a 1 in the 1's column. And in combination, those have a value equal to 3 in decimal. And so you have a 1 and a carryout operation in that case. And so we have all 8 possible combinations. This operation is what a full adder can do. And that's why it's called a full adder, because it can add all 8 of these combinations, including all the carries that come into it. Whereas the half adder can only do this part of the logic, just this first part over here that has no carry bit coming in. And so that is the half adder, right? That one there, and the full adder can do all 8 of those operations. Now, if you think, let me go back here. If you think that looks like a truth table, the reason for that is that it is a truth table. It's just not presented as cleanly as a truth table that we would format like this. Here is the half adder truth table. Let's look at it for a moment and think about it. The half adder has these 2 inputs, A and B, where A can be 0 or 1, B can be 0 or 1, and all 4 combinations of A and B together will produce a sum of 0, 1, 1, or 0, and a carryout of 0, 0, 0, and 1. Now, look at these 2 columns, the sum and the carryout a bit, and tell me what they look like to you. If you look carefully at the inputs and the outputs resemble exactly 2 well-known logic gates. The outputs resemble 2 well-known logic gates. Think about that for a moment. And if you don't know, try to figure out what are the logic gates that are showing up here. If you guessed that the logic gates were the exclusive OR gate and the AND gate, you would be right. 0, 1, 1, and 0 for these inputs is the truth table for the exclusive OR gate. What is the exclusive OR gate? Well, the exclusive OR gate says if either A or B is 1, but not both of them, then the output is 1. Otherwise, the output is 0. And so where you have 0 and 0, the output is 0. You have 1 and 1, the output is 0. You have 0 and 1, or 1 and 0, the output is 1. That's exclusive OR gate. And now look at the carryout operation. This is the AND gate. What is an AND gate? Well, an AND gate says if both A and B are 1, then the output is 1. And all the other cases, the output is 0. That's an AND gate. You can implement a half adder with logic gates by simply putting the inputs of A and B into the exclusive OR and the AND gate. And the outputs would be the exclusive OR will give you the sum, and the AND gate will give you the carryout for that operation for a 1-bit half adder. And I think that's pretty cool. when you see that and realize how that is done. All right, let's look at the full adder truth table. And it's a little more complicated, of course. We got three inputs, the A, B, and carry in. And we got the sum and the carry out operation. And if you look at the this is going to be kind of interesting too. We have this sum here. That's the same exclusive OR. Let me say, I'm sorry. That's the same exclusive OR. I'm pointing to a different part on my screen. I know that you can't see what I'm talking about all the time. But this carry in operation is, this carry in operation is kind of like a selector. And you've got the sum here, which is exclusive OR for these 4 bits. And you've got the sum here, which is just the opposite of these sums. These 4 values here and the 4 values over here are identical to one another. The only difference is the carry in operation. And if you look here for this A and B, you've got the exclusive OR for the sum like we saw in the half adder. Well, this is not an exclusive OR. It is the inverse of an exclusive OR. If you took these values and exclusive OR'd them and then took the inverse, you would get these values here, 1, 0, 0, and 1. Now look at the carry out. The carry out operation is 0, 0, 0, 1. And we saw before that that is just the AND operation for these 4 inputs. And now look at here, 0, 1, 1, and 1. That is the OR operation for these 4 values. So you could use the carry in operation. You could use the same logic that we did before for the sum for here. Take the inverse of that based upon the value of carry in, and then do something similar for the carry out. For the carry out, you can take the AND for this carry out, and then for this one, you can take the, you could use an OR operation and then use the carry in operation to select between the AND and the OR operation's value for the carry out operation. That would just be one way to create the full adder. Now, there has to be some way to represent negative numbers and positive numbers in binary, and there are different ways that can be done. Let me see here. I'll bring my video back so you can see my pretty face. There are different ways that can be done in binary. It depends upon a number of considerations as to how it's done in binary, but we'll look and see how it is normally done and why. One possibility would be to reserve the first bit of a number to represent the sign. And so it would be like the first bit of the number would be a 1 to indicate negative and a 0 to indicate positive. 2 and negative 2 in this for a 4-bit number would look like what we have here with 0, 0, 1, 0. That's 2 in the positive binary, and then in a negative binary, 1, 0, 1, 0. And that is similar to the way that we do it in decimal. In decimal, we just put a a minus sign, or we put a sign out there to indicate negative, and then the same number out to the right for the absolute value that we would use for the positive number. And that's one way that it can work, but there are problems with that logic. Primarily, it makes certain operations more difficult to perform in logic. It can be done, but the logic is more complicated if you use that system. A better way to indicate negative numbers in binary than what we've just seen is what is called the ones complement. And the ones complement is to take the complement of a number as its negation, as its negative. And so with a ones complement, you would take the number 0, 0, 1, 0 and flip each one of these bits, and you would get a 1, 1, 0, 1 for the negative number. And in this case, this is there's some things to like about this particular system, because in this case, these numbers would be, you can add them up and so on in the same way that you would add up the positive integers, and there's not that much difficulty with it, but there is one little complication, and that is, what do you do about this number here? 1, 1, 1, 1. What does that represent? Is that negative 0? Well, it would have to be if this was the system that you were going to use. Better than the ones complement is the twos complement system. And the twos complement system is like the ones complement, except that it differs by adding 1 to the ones complement so that all the numbers are utilized. And counting, for example, from 3 back to -3 in the twos complement system, you would have 0, 1, and 1, which is +3 in digital. 0, 1, 0, or +2. 0, 0, 1 is +1. And then 0, 0, 0, it's neither positive nor negative. And then the next number below 0, 0, 0 is 1, 1, 1. And in two's complement, that would be equal to -1. And one less than that is 1, 1, 0. And that's the -2 in binary. And 1, 0, 1 would be -3. Now, if this in ones complement, this is equal to 0, just like that. And this would be equal to -1, and that would be equal to -2 in the ones complement system. By adding 1 to these numbers, we get this number back, and we have all the numbers that we need. And it just so happens that this system simplifies binary operations because all positive integer operations that you can perform with logic gates work on the twos complement numbers perfectly without doing anything else to them. And so that is one of the great benefits of the twos complement system. All right, that is all that we want to do for our study of binary logic. It's going to help us some, I think, in this week's logic gates. Let's take a look at what is included in this week's challenge. And I'm going to move my picture off again, and we'll take a look. First is the half adder, and this is the order that you want to do them in. You want to do the simplest ones and then build up from there. So we'll start off with a half adder. And this is the stub that you'll get within the folder number 2 in the project folder. And the half adder has 2 inputs, A and B, as we talked about this before, and 2 outputs, the sum, it's also a single bit, and a carry, and that is the result of the carry if there is one. You'll put your parts, list your parts down here in the parts list, and the connections in the way that you learned to do for the first week, and that one should be pretty simple. Just think of the 2 gates that we talked about for the half adder. The full adder, just a little bit more complicated. It's got 3 inputs, A, B, and C. These are all 1-bit inputs. And then it has a 1-bit sum, which is going to be the right bit of A plus B plus C, and 1-bit carry, which would be the left bit of A plus B plus C. So if we're talking about binary, we're going to have 2 bits in the output. The left bit will be the carry, the right bit will be the sum. And just replace that with your parts and connections, and you should be able to do that. The 16-bit adder is just a little more complicated than, oh, wait a minute. Yes, the 16-bit adder is a little more complicated than the adders that we've talked about. But once you build the adders, the 16-bit adder is not that complicated, because you'll just reuse the adders that you've created before. And just put them in a series, 16 bits. The first one will be the 0 bit of the operation. Then you'll have the 1 bit, the 2 bit, the 3 bit, and put the wires up so that the carry from one column goes over into the next column, and so on for the 16 bits of your operation. Remember how to specify the various wires within this 16-bit bus, going from 0 to 15, and you would just take those out, 0, A0, A1, A2, so on, within these brackets, and send those to your full adders. You can use 16 full adders for this, or use 1 half adder and 15 full adders. Either way, it doesn't matter. And then the output of those 16 components will go back to the input of your, or will go to the output here of the 16-bit adder, 0, and you'll just put out 1, out 2, and out 3, so on, for the entire thing. So you just put that under the parts, and it should work out for you. 16-bit incrementer takes your 16-bit adder, and it makes a simple counter for you. Basically, you take the 16-bit adder, put some loopback logic in there so that the last output will be the input for the adder if there is no external input. Let me think about that for a moment. This has an input of 16, an output of 16. An input of 16, output of 16, that's confusing me a little bit. But anyway, let me look to see how I've implemented that, because that is I'm a little confused now by that particular thing. Let's see, going down to projects. Okay. Okay. Okay, I see why. I see what I was having problem there, and let me just show you what this is telling us to do. The incrementer, I was thinking it did something else, but what the incrementer does, it takes the input, whatever that input is, and it adds 1 to it. So you get the input plus 1 to it is the value. And so basically you take a 16-bit adder, you give it this input for one of its inputs. The other input is going to be a constant value of 1, and so the output for the adder will be whatever the input is plus 1. And so that's a pretty simple logic gate for you. And now the most complicated will be the arithmetic logic unit. And this one takes a little more explanation, so just bear with me for a moment and we're almost done with today's video. In the arithmetic logic unit, you're going to be creating a unit with a lot of inputs, several outputs, and it has to do a lot of different things. And it may have to do several different things at the same time. For example, if Zx is equal to 1, then it sets x, the input x, it sets it to 0. And so x is going to be set to a constant value, 16-bit value, where all the bits are 0. If nx is equal to 1, then it sets x equal to not x. And so whatever x is, if nx is equal to 1, then it's going to be inverted, complemented in a ones complement way, where all the bits that are 0 will be 1, all the bits that are 1 will be 0. It is possible for Zx and Nx to be 1 at the same time, which means that x would be first set to 0, and then x will be negated, so all the pins get switched from 0 to 1. If Zy is equal to 1, then it sets y to 0. If ny is equal to 1, it sets y to not y. So the same thing happens here with y that happens with with x, based upon these flags that come into the ALU. If f equals to 1, then that tells the logic unit to perform an addition with whatever values are in x and y. X and y are going to be the value of x and y are going to get their values from whatever is input plus these operations, and then they're going to go through this addition possibly if f is equal to 1. If f is equal to 0, then instead of adding x and y, you and x and y. This is a bitwise and. Obviously, f can only be 1 or 0, so only one of these operations can take place. And then finally, if NO is equal to 1, then you're going to take the output and negate the output. That is the output of this operation here, these two whatever these two operations end up giving you, if NO is equal to X, then it's going to set the output to not out, or it's going to be a bitwise not, and all the bits will be flipped, ones to zeros and zeros to one. Those are all of the operations that the ALU can perform. And what you'll find is that with these various operations and combinations, the way that they can be put together, different things can be done by the ALU. This is the chip inputs. We have two 16-bit inputs, X and Y. 16-bit buses. ZX is a 1-bit input. NX is a 1-bit input. ZY and Y are 1-bit inputs. F is a 1-bit input, and NO is a 1-bit input. And all of these are the pins that will direct the ALU in manipulating the values of X and Y on these two buses. The output is going to go to the 16-bit output called out. There's also an output called ZR, and this is going to be 0 if the output is equal to 0. And this is NG, and this is going to be a 1 if the output is negative. So if this output is negative, basically if pin 15 is a 1, then NG will be a 1. Otherwise, NG will be a 0. In other words, NG is going to be the same value as pin 16 of the output. And so with that understanding of your inputs and outputs and what the logic is supposed to occur within the ALU, you are to determine what parts are needed and the connections that are needed and go from there. What am I missing here? That's the, okay. It's more about the arithmetic logic unit, but I think, didn't we cover that? For some reason, I've got a copy of that in there, I guess. All right, here are the resources for this week. And you'll find these also below the video and the links that you can get to each one of these links from the description for the video that's right below. The head homepage where you can get the head tool that I showed you before, the editor. The digital homepage, this is the digital program, which is a logic gate simulator and designer that you can use. We didn't use it in this video, but we did in the previous one. The NAND to Tetris software you can find here at NAND